Okay, we're going to get started with the next chapter, and this chapter primarily focuses on chemistry of life and how different processes within the body rely on chemistry. So, this section is primarily on just a few terminology that you may be very familiar with already. We all know that when we say matter, that's anything that's going to take up space, has mass. So your pencil that you're holding takes up space and it has mass and is made up of a specific type or types of elements. It may be made up of lead, it may be made up of a host of things. If we're talking about a desk, it may be made up of iron, it may be made up of copper. And so those are elements. And within those elements, we have very small particles that have the same properties of those elements. And those will be atoms. And those are just the smallest particle that can make up an element or matter. And so we have atoms of carbon, atoms of lead, an atom of hydrogen. And when we're talking about elements specifically within the body, we have a couple different groups. The very first group, we have bulk elements. When you think about something bought in bulk at a store, those are items that you buy a lot of. And so bulk elements are ones that we have a lot of within the body. We have large amounts of these within the body. Let me put this on here. So we have large amounts of bulk elements within the body. As far as trace elements, if something is trace, they're in small amounts. So that's a lot different from our bulk elements. And so as far as the bulk elements, carbon, hydrogen, oxygen, we have lots of those that helps make up the parts of the body or just chemicals within the body. And we also have trace elements. These are elements that are found in small amounts, but they're still needed. For instance, iron. Iron is made or found in hemoglobin, and hemoglobin is a protein that is used for the carrying of oxygen throughout the body. So we definitely need iron, but it's found in very small amounts. And then we have iodine. Iodine is also an element that is definitely needed, but iodine is primarily used by the thyroid. And if any of y'all know people that may have like hypothyroidism, that is a result of having or not having enough iron in the body. And that's also one of the reasons why people or companies have started to iodinize salts. Most of the salts that we buy now, you'll see the term iodinized salt on the label because they realized we were not getting enough iron in our everyday diets. And then ultra trace. So anytime you see the word ultra, that just means extreme or a lot. We already said that trace means small. So very small amounts will be elements that we need, but we need very, very, very small amounts. For instance, arsenic. Arsenic, if y'all know anything about that, can be deadly. If we have too much arsenic, it can poison us, it can kill us, but we still need it. We still need it for certain reactions and certain processes that happen within the body. So let's talk about atoms in general, or just the structure of atoms. And so when we talk about the structure of an atom, we have protons, neutrons, and electrons. Those are subatomic particles, and each one of them have different charges. They're located in special places that may be different from the others. And so protons are going to be positively charged. They're going to have a positive charge. And they're going to be located inside the nucleus. So we have protons here, we have proton here, proton here. And then we have our neutrons. Our neutrons are neutral. They have a neutral charge, and they're also going to be located within the nucleus. That's what these structures are representing. And they're found inside the nucleus as well. And then we have our electrons that are going to be negatively charged. They have a negative charge, and our electrons are found orbiting around the nucleus. So they're on the outside of the nucleus. Okay? So they have a negative charge, whereas protons are positively charged and neutrons are neutral. Now I'd like to ask the question now, if we have positively charged protons and we have neutral neutrons, and these are both inside the nucleus, what charge does the nucleus have? What charge does the nucleus have? The nucleus, of course, is going to have a positive charge, okay? Because we have positively charged protons and we have our neutral neutrons that are found in the nucleus. Okay? So, if y'all ever looked at the periodic table, you notice it is filled with numbers. One of the numbers that we find on the periodic table is the atomic number. And the atomic number is going to show us the number of protons. Remember, these are found in the nucleus, and they're positive. But this is going to be the amount of protons that we have. Okay, so for instance, if you were to pull up a periodic table, you will see that oxygen has an atomic number of 8. So if oxygen has an atomic number of 8, that means that oxygen has 8 protons. Or carbon, that has an atomic number of 6, carbon has 6 protons. So another question I like to ask is, if atoms are electrically neutral, that means the entire atom is electrically neutral. And remember, neutral means that it has no charge. Okay? If the entire atom is electrically neutral, what must the atomic number also equal? I'm going to give you all a few seconds to kind of think about that. What must the atomic number also equal if the entire atom is neutral? Now, we just said that the atomic number is equal to the number of protons, right? And protons are positively charged. So again, if the atom is electrically neutral, what must the atomic number also equal? So hopefully you're thinking, if protons are positive, in order for that to be neutralized, we must have the same number of negatively charged particles. And so in order for this to be neutral, this must also equal the number of electrons. So for instance, and this is the atom initially. We're not talking about if it's losing or gaining electrons. Initially, as it is found, oxygen has 8 protons. So that means that because oxygen is electrically neutral, it's going to also have 8 electrons. Carbon, 6 protons, which means that carbon also has 6 electrons. Another number that you'll see on the periodic table is the atomic weight. The atomic weight has to do with the mass or the weight of the atom, and this is going to be our protons plus our neutrons, because they are the particles that take up most of the mass. So remember, we have protons, we have neutrons, and we also have electrons. And so why don't electrons factor into all of this? Is because they're so light that they do not contribute to the weight of the atom. Because they are so light, they do not contribute to the weight of the atom. Okay? So, you have protons in the nucleus. You have neutrons in the nucleus, electrons orbiting around. And we know that our atomic weight is going to come from protons plus our neutrons. Now, another term that you may have heard is isotope. An isotope is going to be an atom, or that same atom, but it has varying amounts of atomic weights. Now, one thing that cannot change, one thing that will never change, will be the number of protons. The number of protons never changes. However, the number of neutrons can change. And so when the number of neutrons vary, that means that the atomic weight will then vary. For instance, if you look at the periodic table under oxygen, the atomic weight is about 16 point something. There's a decimal there. That is because it is an average of the isotopes for oxygen. So, we already know that oxygen has the atomic weight, or not atomic weight, it has atomic number of 6. That means it has 6 protons. Let's say there is an isotope of oxygen that has also 6 neutrons. That means that the atomic weight for that atom is going to be what? Will be 12, right? But we also can have another isotope that has, of course, 6 protons, because the number of protons will never change, but it may have 7 neutrons. If it has 7 neutrons, that means that the atomic weight is now 13. And we may even have one that has 6 protons. And I'm sorry, you all, I'm using 6 for oxygen, but carbon actually has 6. So to fix this, let's say we're not using oxygen, but we're using carbon, just so that we are correct chemically. We're using the right terms and the right elements, but it's still the same concept. So carbon will have 6 protons and 6 neutrons. This isotope will have a weight of 12. Carbon that has 6 protons and 7 neutrons, that carbon will have an atomic number of 13. We also have carbon with 6 protons and, let's say, 8 neutrons. And that isotope of carbon will be 14. So the number that we see on the periodic table is an average of those atomic weights. It depends on which one is found the most on Earth, if the one that has an atomic weight of 12 is found most common, then you may have the atomic weight that's closer to 12. If it's the one that is 14, you may have an atomic weight that is closer to 14. Okay, so that's basically what an isotope is. We have varying numbers of neutrons. The neutrons will change, protons will never change. And let's say we were going to use the oxygen example. We have oxygen always will have 8 protons. Let's say we have 8 neutrons. That's going to be an atomic weight of 16. Another isotope could be 8 protons, 9 neutrons. That will be an atomic weight of 17. Let's also say maybe we have oxygen with 8 protons and 7 neutrons. There'll be an atomic weight of 15. And the average of those is what we see on the periodic table. So, other terms, molecules and compounds. When we're talking about a molecule, this is going to be specifically when you just have 2 or more atoms that are together, that are bound. For instance, if we have 2 hydrogen atoms or 2 oxygen atoms, that's going to be a compound. Not a compound, a molecule. A compound is when we have different atoms from different elements together. So, an example would be H2O. So we have a atom of oxygen and 2 atoms of hydrogen. These are 2 or more of different elements. Okay? And so compounds can technically be molecules because we have 2 or more atoms chemically combines. But with a compound, it's specifically with different elements. Okay? So H2O is a molecule, but specifically is a compound. O2 could not be considered a compound, but it is a molecule. Okay. We also have molecular formulas, and this is what I wrote here and here. This just tells you the number of each atom that's present in that particular molecule. For instance, when I write H2, that means that we have a molecule of hydrogen, but we have 2 hydrogens. And C6H12O6, that means we have 6 carbons, 12 hydrogens, and 6 oxygens, and that's glucose. And the same thing for water, which is what I referred to earlier, having 2 hydrogens and 1 oxygen. And this is just a depiction or image that shows molecules and compounds, whereas molecules is literally just 2 atoms that are bound together, like O2 or H2, whereas with a compound, you have 2 different atoms from 2 different elements. A compound is formed, but this compound is also considered to be a molecule. So this brings us to, since we've talked about our atoms, how do we make these molecules and compounds? We're going to go through talking about bonding. And so the way that elements or atoms bind to each other is through bonds, but specifically they use their outer electron shells. And it is important to note the amount of electrons that can be found on each shell. The first shell can hold up to 2 electrons. And if there are only 2 electrons that are needed to be placed, then that it will only have 1 shell. The second shell can hold up to 8 electrons. So you can have 2 on your first, 8 on the second, you can have up to 8 electrons on the third. And this is what we consider to be stable. Now, there are other rules that may apply when it comes to atoms that are a lot larger, but we won't go into a lot of detail with that for this class. But you do need to know that if it is 18 or less, first shell is 2, second shell is 8, and third shell is also 8. So, when we're talking about the bonding of atoms, there are a couple different structures that are going to be formed, or a couple different molecules and structures that will be formed. And so the first term that we're going to talk about would be an ion. And so an ion is going to be an atom that has either gain or loss electrons so that it can become stable, so that its outer electron shell can be stable. And then if it loses an electron to become stable, we call that a cation. And so if it loses electrons, remember electrons are negative. So if it loses an electron, it's going to become more positive. Okay? If it loses electrons, remember electrons are negatively charged. If it loses electrons, it's going to become more positive. And on the opposite side, if it gains more electrons, remember electrons are negative, if it gains more electrons, it's going to become more negative. Okay? And the way that I've always remembered this, and if it works for you, great. If it doesn't, that's fine as well. But positive makes me think of a positive sign or a plus sign. And so the cation has this T, and this T sort of looks like a plus sign. Whereas with anion, it has the N. That reminds me of being negative. So cations, positively charged from losing negativity, losing these negative electrons, whereas an ion is a negatively charged ion because it has gained more negatively charged electrons. Okay. Next, when we have these ions, when we have these positive and negatively charged ions, they're now charged. They're either positive or negative. And so now they are attracted to each other. And so positively charged ions are going to be then attracted to negatively charged ions. And they're going to form an ionic bond. So when that cation that's positive and this anion that's negative, they are now attracted to each other. And the example that is here is sodium chloride. I'm going to write this off to the side because sodium has this positive charge, whereas chlorine has a negative charge, and they make sodium chloride, or NaCl, which is basically salt, table salt, the salt that we eat. And then we have covalent bonds. Covalent bonds is going to be where we have the sharing of electrons. They're not just giving electrons and taking them away, but it's sharing electrons. That's the key thing here. And so they're not, again, giving electrons or taking electrons. Those electrons are being shared by a pair of atoms. For instance, with this molecule of hydrogen, it has one electron on its outer shell. But remember that first shell can hold up to 2, all right? And so both of them want to have 2 electrons on the outer shell. And so they can now share that. And now if you look at this one, this atom, it has 1, 2 electrons. If you look at this one, it also has 1, 2 electrons. And so they're now both stable. And this will be our hydrogen molecule. And this is just another example where we have the formation of water. We have our hydrogen atoms here. We have our oxygen atoms that are here. And if you were to look at the end result of H2O, remember the first shell can hold up to 2. This is our oxygen atom here. It has its 2, but now oxygen has on its second shell that can hold up to 8. 1, 2, 3, 4, 5, 6, 7, 8. So it's stable. And hydrogen that only has 1 shell that can hold up to 2 has 1 and 2. Same thing for this one. 1, 2. And so now that both molecules are sharing their electrons, they're both stable. So another way that we can show the bonding of atom is through its structural formula. And the structural formula will show us the types of bonds as well and how they are arranged. If the shape of the molecule is different, or it could be just showing the number of bonds that are between 2 atoms. For instance, with H2, we see 1 single bond here. That's a single bond. With this one, we have a double bond. The 2 lines show a double bond. This shows that we have a single bond between hydrogen and oxygen, both sides. And then with carbon dioxide, we have a double bond between the carbon and each of the oxygens. And so it just kind of shows the way that they are arranged, the way that they bond by having those lines there, and even the shape. So when atoms share electrons, sometimes they don't always share them equally. Sometimes it may be a bit of unequal sharing, whereas some of the electrons that are being shared are being pulled closer to one molecule or one atom more than the other. And the perfect example that is usually shown for polar covalent molecules is water. With water, there is an unequal sharing of electrons where one atom, in this case, the oxygen atom, pulls the electrons closer to it more than the hydrogens. They're still sharing, but the electrons are being pulled closer to the oxygen. And the reason being is because the oxygen atom, if you remember, we just talked about it, it has 8 protons. And since it has 8 protons and hydrogen only has 1, the electrons are attracted to oxygen a lot more than they are to hydrogen. So this end it has 8 protons. And so the electrons want to be pulled closer to it from both ends. And so this makes this end slightly negative, whereas this is going to be slightly positive. And it has all to do with the oxygen having more protons in its nucleus. Another type of bond we have is a hydrogen bond. And a hydrogen bond kind of works with our water molecules that are going to allow the positive end of a hydrogen to be attracted to the negative end of another molecule. And in this case, from the picture, the other molecule is oxygen. Remember, we were just saying that the oxygen is slightly negative and the hydrogen is slightly positive. And so that charge on those molecules will cause the molecules to be attracted to one another. So this is a single water molecule, but to pull it to another one, we have a hydrogen bond. And so one thing that I want to make sure that I make clear, to hold together a single water molecule, that is a polar covalent, and that is what we were talking about on this slide. It's a polar covalent molecule that holds together a single water molecule that holds together one molecule of H2O to make sure that these hydrogens are being held together with this oxygen. But we know when we see water is not just that, it is multiple water molecules. And so we have to have a type of bond that's going to hold them together. And the type of bond that will hold together multiple water molecules is a hydrogen bond. So to hold this water molecule to this one, this bond, this bond, this bond, those are hydrogen bonds. All right, so now we have compounds and molecules, and we've talked about how they bond or how they bond with each other, but we know that there's a little bit more that goes along with it. There's going to be a ton of reactions that happen in the body, and with those reactions, we have two main players. We have reactants and products. If we're trying to, for instance, break down a compound, in this case NaCl, this will be the reactant. This is what we start with. So the reactant is whatever you start with. And then the product is whatever you end with. And so if we're breaking down sodium chloride, we'll end with an atom of, or an ion of sodium and an ion of chlorine. This could also go in the other direction. For instance, the reactants could be sodium and chlorine, and the products could be sodium chloride. Okay? So, whenever we have reactions, we have different types of reactions, but we're going to talk a little bit about acids, bases, and salts. And whenever you have a type of molecule or compound, if you were to put that compound inside of water and it began to dissociate or come apart and release ions while in water, we call that an electrolyte. You all probably have heard of electrolytes before. I know they have electrolytes in Gatorade and Powerade. We have to have electrolytes for our bodies to function. And so electrolytes dissociate or release ions in water. And we have a couple different types of electrolytes. We have acids and we have bases, or we have acids that are going to release hydrogen ions in water. So an example of this will be hydrogen chloride. When placed in water, it releases this hydrogen ion, or hydrofluoric acid that release that hydrogen ion in water, or sulfuric acid that will also release that hydrogen ion in water. So those are acids. And then we have bases. They're going to release ions that can then combine with hydrogen ions. And the specific ion that they release is this one. So this is a base right here. And this is the ion that can combine with a hydrogen ion. This ion is called a hydroxide ion. And a hydroxide ion can then combine with a hydrogen ion to form water. And then we also have salts. Salts are also electrolytes, but they're formed whenever you have an acid. Here, this is the acid, and a base, which is here. Whenever they combine, they form water and a salt. Remember, we said that when these two dissociate, the acid is going to release the hydrogen, the base is going to release this hydroxide. These two will combine to form water, whereas sodium and chlorine will then combine to form the salt. And this is just a diagram or image that shows exactly what we're talking about. This is sodium chloride. If placed in water, will dissociate, and the water will break apart that molecule into sodium and chlorine. So another way that we kind of describe acids and bases based on their concentration and or their chemical concentration, and we have to make sure that those concentrations of different acids and bases are at a level that is optimum for that organism. And so the pH scale is what we use to determine, not really determine, but to measure the acid-base concentration, specifically the ion concentration. And that's what pH kind of stands for, is the percent of hydrogen. And we know that it's a 0 to 14 scale, whereas 0 is towards the acid end and 14 is the most basic. If it's less than 7, it's an acid. Greater than 7, it's a base. And then 7 is neutral. And that's where water is that typical 7, although sometimes the water that we drink is a little basic or maybe a little acidic. And this is just another depiction of how the ion concentration changes as pH changes. So pH of 0 grams of hydrogen per liter is 1, but if you notice, the grams of hydrogen ions per liter gets smaller and smaller and smaller as it becomes more basic. So within the body, we have to make sure that things are not too acidic and it's not too basic. When things become too acidic, that is called acidosis, which we don't want to be, because this is where the pH of the blood drops below where it should be. So the pH of blood is very slightly, very slightly basic. But if it drops below 7.3, it is called acidosis. And you may feel a bit tired, kind of disoriented, and it may cause a bit of vomiting as well. Or it could be caused because you have vomited some alkaline solutions or contents from your body. And so when you are removing those alkaline contents, then your blood may then become more acidic. Same thing for alkalosis. If you are vomiting and taking out too much acids in your stomach, that could cause your stomach to become too basic. Also, where a person may become a bit dizzy or even a bit agitated. And of course, we have mechanisms, and if you all remember, we talked about this previously, whereas if we become too hot, then our body will bring us back down. If I'm too cold, will bring us back up. If our body becomes too acidic, we have mechanisms in our body that is going to bring us back towards basic and vice versa. Okay, so this next section is talking about the different types of molecules that we have within the body. And we have organic and inorganic molecules. As far as organic molecules are those that are going to be primarily carbon and hydrogen. And they're going to be things like our carbohydrates, our lipids, and our proteins. And with our carbohydrates, lipids, and proteins, we'll talk more about those, but they don't release any ions, they're non-electrolytes, but we'll spend a lot of time talking about organic molecules later on. As far as inorganic molecules, they're not going to have carbon and hydrogen. They're not going to, or they are going to dissociate, which is opposite of our organic molecules. So these are things like our waters and our oxygen, carbon dioxide, things that we still need within the body, but they're considered inorganic molecules. So some of the inorganic substances one of the ones, or a couple of them, are water, which is the most abundant compound in the body. Actually, about 70% of the body is made up of water. So we have to have this for a lot of our metabolic reactions. We have to have this for heat transportation and keeping the body in the temperature that it needs to be, and just water balance in general. Next, oxygen. You can probably imagine why we need oxygen, why it's so necessary for survival. It's so that we can go through respiration and we can go through or create ATP and so forth. Carbon dioxide also is a substance that we have within the body, but in this case it's a waste product or a byproduct of respiration, and we get rid of that when we exhale. And then we have some inorganic salts. For instance, when we're talking about sodium and chlorine, these are the ions that are needed to create these inorganic salts that we have, or it could be potassium chloride or calcium chloride. These are salts that form to help with metabolism, also water concentration, because usually wherever salt is, water will follow. So they'll help kind of regulate the amount of salt we have as well. All right. Okay, so for our organic substances, the very first one we have is carbohydrates. With carbohydrates, this is going to be our main source of energy. This is where we get most of our energy. And we have also, it's going to have a very specific ratio. We have carbon, hydrogen, and oxygen, just like all of the other organic molecules, but it has a very specific ratio of hydrogen to oxygen that is about 2:1. For every 2 hydrogens, there's 1 oxygen. And the example of that would be glucose. For every 2 hydrogens, there's 1 oxygen. Very important that you all remember that ratio for carbohydrates. Very, very important. So other examples, we can kind of classify them based on how complex they are. We have monosaccharides, which means 1 sugar. Say single sugar. Saccharide means sugar. Di means 2 sugars. And so monosaccharides are glucose and fructose, whereas disaccharides are double sugars, sucrose, lactose. Sucrose, example, that's our table sugar, the sugar that we have in our homes. Lactose is the sugar that we find in milk. And polysaccharides, many are very complex sugars. These are the ones we find in like starches, glycogen, which is stored in the liver. Cellulose is found in plants, which is something that we try to break down when we eat plant matter. And this is just another way to show different carbohydrates, specifically glucose. This is that structural formula of glucose. This is also a glucose ring, but this one is glucose, but not showing all of the compounds that stem off from it. And this is showing our monosaccharide, one sugar, disaccharides, two sugars joined together, and our polysaccharide, which would have many sugars that are bound together. The second type we have our lipids. Lipids are our fats. And so with lipids, a lot of times they are used for energy if need be. If we kind of run out of carbohydrates or we don't have enough. And so our lipids are going to be those that are organic, but they are fatty, so they can't be dissolved in water. And so the most abundant ones are our triglycerides, and triglycerides just means that we have 3 fatty acids and a glycerol, which is going to, I think, show up on the next slide, but consists of the glycerol and 3 fatty acids. And we also have carbon, hydrogen, and oxygen, but the ratio is going to be a little bit different. Whereas with carbon, hydrogen, oxygen, remember we have that 2-to-1 ratio. For every 2 hydrogen, we have 1 oxygen, but we have a lot less oxygen in our lipids than we do in our carbohydrates. And we also have 2 ways of classifying our lipids. We have saturated lipids or saturated fatty acids and unsaturated fatty acids. Saturated fatty acids are going to be those that are full of single carbon to carbon bonds. So it only has all the carbon to carbon bonds are single bonds. So it's saturated or full of carbon to carbon bonds. Whereas unsaturated fats are going to be where we have at least 1 carbon to carbon double bond. And in this example, we have a carbon to carbon double bond here, we have 1 here. And so if you have at least 1, it's considered unsaturated. Saturated, the word saturated, to me means it's full of something. And so in this case, we're talking about full of carbon to carbon single bonds. But if we have at least 1 double bond, then it's not considered a saturated fat. And most of our saturated fats are those that are going to be solid, like the white Crisco, the lard, butters. Unsaturated fat are going to be those are like vegetable oils, avocado oils, things like that. And this is the picture that I was referring to, the triglyceride, where we have a glycerol backbone and 3 fatty acids. We also have phospholipids, and you'll see a lot more about phospholipids when you talk about the parts of the cell, specifically the cell membrane, because it's made up of phospholipids. But the phospholipid is going to have also a glycerol, and in this case, 2 fatty acids and a phosphate. So this is our triglyceride, glycerol backbone, 3 fatty acids. But this one, glycerol backbone, 2 fatty acids, and a phosphate. So that's why we call it a phospholipid. It also has very hydrophilic ends and hydrophobic ends. The hydrophilic means that it's water loving, and that's going to be the head. So this is water loving or soluble, that's going to be hydrophilic, whereas the hydrophobic, which means water fearing, these are going to be the tails. So that's why they're very important when it comes to cell membranes and the way the cell membranes form, and it controls things going in and out of the cell very well because of the structure of phospholipids. In addition, we also have steroids, which is just another type of phospholipid. And we have them all over. We have them within the cell membrane. We have them, they are going to be used to synthesize a lot of our hormones. The adrenal glands that are found on top of the kidneys, lipids or steroids specifically help to synthesize those, and things like testosterone and estrogen as well are steroid hormones. And the main hormone that we have, or not the main hormone, the main steroid that we have in the body is cholesterol, which we may talk more about later on in A&P. All right, so we've talked about carbohydrates, lots of energy, lipids, that's our fats, and now we're going to go to our proteins. With proteins are going to have a wide range of purposes and functions. They're for energy, hormones, antibodies, a wide range of things. But the building block of a protein is an amino acid. Okay, so the basic structure of a protein that helps to make it is an amino acid. Okay, and so many amino acids help to make up a protein, or a group of amino acids help to make up a protein. And usually, an amino acid is going to have an amino group, a carboxyl group, and a side chain. Okay, again, this is just showing our different groups that are found on an amino or found in a protein. The amino group is in reference to the nitrogen and hydrogen. Carboxyl, anytime you see carboxyl, that's the carbon, 2 oxygens, and the hydrogen, and the R side chain group. So we have our R side chain groups, we have our amino group, and our carboxyl group as well. And this is just the basic structure of a protein. And amino acids have to be bound to each other, and they also have a special type of bond. Now, we talked about bonds before, but these have a special type of bond, and that's called a peptide bond. And this joins together amino acids. And so when we talk about a protein, it has a couple different structural shapes. The first one is a primary shape, and when I kind of think about primary shape, it's just flat, straight amino acid sequence. The example that I usually use in class, where we have a sheet of paper that is flat, that will be the primary. If we were to take that sheet of paper and fold it like this, that's the secondary structure. So it starts to change shape. That's when more than one amino acid chain binds to another. Then our tertiary sequence is when that starts to kind of fold upon itself, kind of fold into this 3D structure. And then quaternary is when we have multiple proteins are bound to each other to become one big protein, like the hemoglobin molecule or the hemoglobin protein. And our very last organic compound is nucleic acids. With nucleic acids, the two that we have are DNA and RNA. DNA is going to be responsible for our genetic information, whereas RNA is going to be responsible for protein synthesis. We'll go into a lot of detail with that later. But the building block of a nucleic acid is a nucleotide. So these are what help to make up nucleic acids. And the nucleotides are going to be made up of a sugar, a phosphate group, and a base. And that's basically what this picture shows. We have our sugar, we have our phosphate group, and we have our base. Okay? And that's going to be the building block of a nucleic acid. And the two nucleic acids, again, that we have are DNA and RNA. And they're structurally different. We'll talk more about that. But with DNA, it's called deoxyribonucleic acid, and we have two chains of nucleotides that are bound in the middle, whereas with RNA, we just have one chain of nucleotides. And this picture shows RNA with that one chain of nucleotides bound together, whereas with DNA, we have two chains. This is one chain, and this is the second chain, and they're bound here. Other differences between the two, again, I said about DNA being responsible for genetic information, whereas RNA is responsible for protein synthesis. DNA is deoxyribose nucleic acid. RNA is ribose nucleic acid. The name changes because of the sugar. It has the sugar deoxyribose, whereas this RNA has the sugar ribose. Also, like we just mentioned on the last slide, DNA is a double-stranded molecule, whereas RNA is single-stranded. But both of them, the building block of both, are nucleotides. And that is the end of this section.